All right, let's get right into it. This is our deep dive into synchronous generators, Part 1A. We're going to cover the absolute fundamentals, how they're built, and the physics that locks together their speed and frequency.
Think about massive power projects, like Ghana's Akwasambo Dam,
or Nigeria's giant Egbin power station, or even the entire UK national grid. So what is the one piece of technology that underpins all of them? Every single one runs on synchronous generators. And today, we're going to break down the complete physics behind how they work. Okay, let's jump in.
First things first, to really get how these machines tick, we've got to pop the hood and look inside. We're going to start by deconstructing the core components.
So, inside every synchronous machine, you've got two main players. First, you have the field windings. These are on the rotating part, the rotor, and we feed them DC current to create a really powerful electromagnet. Then you have the armature windings. They're stationary, built right into the machine's frame, or stator. And this is where the main three-phase AC voltage we want actually gets generated.
So here's the magic, right? We create the spinning electromagnet, that's our rotor, juiced up with DC. As this magnet spins, its magnetic field lines literally slice through those stationary coils of the armature. And Faraday's law of induction tells us that this changing magnetic field is going to induce a voltage. And because those armature windings are spaced out perfectly around the stator, what we get is a beautiful, balanced three-phase AC output.
Now that spinning electromagnet, the rotor, it actually comes in two main flavors. On the left, you're looking at what's called a non-salient pole rotor. And on the right, that's a salient pole rotor. I mean, you can see the physical difference right away just by looking at them.
And this is a perfect example of form following function. The non-salient or cylindrical rotor has its windings tucked into slots, making it a smooth, solid cylinder. This design is absolutely crucial for handling the massive centrifugal forces and minimizing wind resistance at really high speeds. Think 3,600 RPM in a steam turbine. On the other hand, the salient pole rotor, with its poles literally sticking out, is perfect for the slower, high-torque world of things like hydroelectric dams. Because it spins slower, you can pack a lot more poles onto it to get the frequency you need, and we're going to come back to why that's so important in a bit.
So we have this powerful electromagnet spinning at incredible speeds. But that brings up a really big engineering problem. How exactly do we feed DC power to a component that's rotating thousands of times a minute?
I mean, really think about that. How do you get direct current to a constantly spinning electromagnet? You can't just attach a wire, right? It would just twist up and snap in a fraction of a second.
Well, engineers came up with two main solutions. The old-school method uses slip rings and brushes. You basically have stationary carbon blocks that ride on rotating metal rings on the shaft. It works, sure, but it's a constant point of wear. It needs a lot of maintenance, and you lose power across the brushes. So for all large modern generators, they use a much more elegant solution, the brushless exciter. It gets rid of all mechanical contact, which boosts efficiency and slashes maintenance.
And this is where things get really clever. Check this out. A small AC generator, called the exciter, is mounted on the exact same shaft as the main generator. Its three-phase AC output is then fed into a rectifier circuit that is also spinning on the shaft. That circuit turns the AC into DC right there on the rotor and then feeds that DC directly into the main field windings. There are zero brushes, zero slip rings, zero mechanical contacts. It's a brilliant self-contained system, and it's exactly why it's the standard for every large generator built today.
Okay, so we've covered the hardware. Now let's get to the heart of it, the synchronous part of the synchronous generator. We are going to derive the single most important equation that governs these machines, and we're going to do it right from first principles.
The whole derivation starts from this one simple physical fact. An AC sine wave completes one full cycle, that's 360 electrical degrees, every single time one pair of poles, a north and a south, passes by a winding on the stator. So that's one electrical cycle for every pole pair.
So if we want to find the electrical frequency, which we'll call Fe in cycles per second or hertz, all we have to do is multiply the mechanical speed in revolutions per second by the number of electrical cycles we get for each revolution. It's pretty logical, right?
Okay, let's break this down into its two parts. First, the revolutions per second is easy. It's just the mechanical speed in RPM, we'll call that NS, divided by 60. Now for the second part, cycles per revolution. Well, that just depends on how many magnetic poles, P, are on the rotor. Since we get one cycle from a pair of poles, the total number of cycles in one full spin is just the total number of poles divided by 2.
And now we just plug those two pieces back into our main idea. The electrical frequency Fe is equal to Ns over 60 multiplied by P over 2.
And when we simplify that, we get the fundamental equation of all synchronous machines. The electrical frequency, Fe, equals the mechanical speed, Ns, times the number of poles, P, all divided by 120. This relationship is not a suggestion, it's locked in by the very physics of the machine.
So, what does this rigid relationship actually mean in the real world? Well, let's run the numbers. If you're on a 60 Hz grid, like in North America, and you have a 2-pole generator, it must spin at exactly 3,600 RPM, no faster, no slower. If it's a 4-pole machine, exactly 1,800 RPM, and if you're on a 50 Hz grid, like in Europe, that 2-pole machine has to spin at precisely 3,000 RPM. The speed is absolutely dictated by the grid frequency you need and the number of poles you built into the rotor.
And this right here is the most critical takeaway. There is absolutely zero wiggle room. Every single synchronous generator connected to the power grid, it doesn't matter if it's hydro, nuclear, or gas, it must rotate at its exact, mathematically defined synchronous speed.
So what happens if one generator tries to slow down? The very instant its output frequency dips below the grid's frequency, it stops being a generator and it actually starts acting like a motor. It starts pulling power from the grid, and that creates a torque that instantly yanks it back up to speed. It's this beautiful, self-correcting mechanism that keeps the entire grid locked together in perfect time. Of course, you have sophisticated governor controls on the engines managing power input to keep that balance just right.
So, to wrap up Part 1A, we've covered the core construction, and we've derived that fundamental speed-frequency relationship Fe equals NSP over 120. In Part 1B, we're going to build on this to explore the internal generated voltage and a really fascinating effect called armature reaction. I'll see you there.